Good morning students. Today we will have the video lecture on design of serial adder with Mealy machine model, and the next video lecture will be Murray machine model. So I want you to make a note, take your notebook, and this is something similar to the class, and please understand whatever I am teaching you in the video lecture will not be repeated in the classroom. So we will start with the design of serial adder with Mealy machine model. So before that, if you have two, if I want to add two 4-bit numbers, say for example my addend is 1011 and my augend is 1001, say for example. So manually what we do here is we will start from LSB 1 plus 1, 0 is my sum, 1 is my carry, which I will take to the next previous bit. Then again 1 plus 0, 0 is my sum, 1 is my carry. Now 1 plus 0, 1 is my sum, 0 is my carry. Now 0 plus 1, 0 is my sum and 1 is my carry. Okay, so what I actually did was I am starting from LSB, slowly propagating my carry one by one to the end and completing at MSB to get my sum and carry. This is the manually I will add two 4-bit number. Okay. Whereas in combinational logic, I hope you all remember, we have studied something called parallel adders. In parallel adders, what we were having is we have 4-bit full adder plus some combinations for performing carry look ahead generator. So this carry look ahead generator, what it will do is it will generate all the intermediate carry and also the output carry. So since it is generating all the intermediate carry and output carry, once you give the addend bit and augend bit, you are able to get the sum and carry immediately without any delay. Okay. Whereas in manual additions, what we are doing is we are starting with LSB. And once you compute the LSB, the sum and carry, which is propagated to the next shift and next shift and next shift, so it takes some time, delay time. Okay, so this is what exactly we are going to do in serial adder, and what you have studied earlier is the parallel adder. Okay, so you need to first understand what is the difference between serial adder and parallel adder. In serial adder, only one bit addition at a time. But here simultaneous addition, no one bit. It means that once you give the augend and addend, it will perform the addition operation and give you the result immediately. Whereas in serial adder, what it will happen is you are giving LSB first, the result will come out and the carry will be propagated, carry will be stored for the next addition. And again the results will come out, carry will be stored for the next operation until the MSB is happening. Okay, so here only one bit addition at a time, whereas here simultaneous addition at a time. Okay, this is the first difference. And the second difference is complexity. This one is complex, very complex circuit, because to perform 4-bit addition you need 4-bit full adder, 4 full adders, plus look ahead carry generator, LACG. These two are very important to perform the 4-bit addition, whereas here you need only one full adder plus one memory. One memory is for what? For storing the carry value, that is, it can be one single flip-flop. Okay, so this is enough. So the difference between serial addition and parallel addition is, in parallel addition there is no waiting time, because once you give the input you will get the output. But in serial addition, processing time is there, so you need to wait for getting the output, because here you are having as many number of bits are there, as many number of full adders and look ahead carry generated. So once you give the input you will get the output in parallel addition. In serial addition you need to wait for a long time, and if it is a very long number of bits, the waiting time is directly proportional to number of bits of addition. But the circuit is very, very simple. Okay, so this is the difference between serial adder and parallel adder. Now let us design the serial adder with Mealy machine. In the sense, we will start with the state diagram. So to draw the state diagram here, what you need to understand is, this is a Mealy machine. So the output should be during the transition between the state. The output is the sum and the carry is in the memory. Okay. Carry will take two forms, either 0 or 1. So accordingly, you will have two states. One is state S0, which tells you carry is 0. Another one is state S1, which tells you carry is 1. So two states we are having in the model. One is state S0 for carry is 0. Another one is state S1 for carry is 1. Only one single bit addition operation we are going to perform at a time. So we will give the inputs in serial manner only. So let us say X and Y are the representation of the input bits. This is addend, X is addend, Y is augend. So this X and Y, two possible input combinations are there. So we will have four possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. Four possible combinations are there. So what we need to do is, from state S0, what will happen if all the four combinations comes place? From state S1, what will happen if all the four possible combination comes place? So you need to work on with that, and you need to complete the state diagram. So for performing the serial addition operation using Mealy machine model, only carry is the thing which you are going to store. So carry can be 0 or 1. So only two states you were having. Now say for example, we are starting from the state S0. In the state S0, carry bit is 0. Now what will happen if input is 0 and 0? That is the first combination is coming into picture. If input 0 and 0 is coming, then 0 plus 0 plus 0 gives you sum is 0. So output is 0. Carry is also 0. So it will remain in the same state. So input is 0 and 0. Sum is 0 and carry is 0. So it will remain in the same state. Now next is, what will happen if 0, 1 is coming? If 0, 1 is coming, 0 plus 1 is 1, 1 plus 0 is 0. Sorry, 1 plus 0 is 1. So if 0, 1 is coming, sum is 1 but carry is 0, it will remain in the same state. Okay. Similarly, if 1, 0, the next combination is 1, 0. 1 plus 0 is 1 and again carry is 0. So 1 plus 0 is 1. So 1, 0 is also 1. Sorry, here also sum is 1. Sum is 1, carry is 0, so it will remain in the same state. Now from this state, the final combination, if 1, 1 comes from the state S0, at which the previous carry is 0, now the input is 1 and 1, the sum will be 0 and the carry will be 1. Since the carry is 1, it will move to the next state S1. Okay, so from state S0, if 1 and 1 are the input, it will go to the state S1 with the output is 0. So because 1 plus 1 is 1, 0, 1, 0 plus 0 is 0, 1, 0. So 0 is your sum, 1 is your carry. It will go to the state S1. So now you completed all four possible combination of the input from the state S0. Similar way, you need to complete all four possible combination from the state S1. Okay. So let us start from the state S1. From S1, if 0, 0 is the first combination. If 0, 0 comes, what will happen? 0 plus 0 is 0. Here the previous carry is 1. Therefore 0 plus 1 equal to sum is 1, carry is 0. So carry is 0, it goes to the state S0. Sum is 1. Okay, so from S1, it will go to S0. If the input is 0 and 0, the output is 1, carry is 0. Now the next combination, 0, 1. 0 plus 1 is 1, already carry is 1. So 1 plus 1 is 1, 0. So sum is 0, carry is 1. So if 1, 0 is coming, sorry, 0, 1 is coming, then sum will be 0 and it retains in the same state because carry is 1. Similarly, if 1, 0 comes, if the input combination 1, 0 appears, then again 1 plus 0 is 1, 1 plus 1 is 1, 0, sum will be 0 and carry will be 1, it remains in the same state. Okay, and final combination 1, 1. 1 plus 1 is 1, 0, already carry is 1, so 1, 0 plus 1 is 1, 1, sum is also 1, carry is also 1. So from the state S1, if the input is 1, 1, the output is 1, retaining in the same state because carry is also 1. Okay. So now you completed all 4 possible combinations of the input from the state S1, all 4 possible combinations of the input from the state S0. Okay. So this completes the state diagram of the Mealy machine. Now the next step is, after completing the state diagram, you need to draw the state table. So for drawing the state table, you need to understand how many flip-flops are required for implementing this circuit diagram. So since you are having only 2 states, 1 flip-flop is enough to implement the circuit. Okay. So to implement the sequential circuit, 1 flip-flop is enough. So let us consider the D flip-flop implementation, because we just want to store the carry, previous carry, to give it as a carry input for the next stages. Okay. So D flip-flop is enough for this one. So when you draw the state table with the D flip-flop, you will have input, 2 inputs, one is addend X, next one is augment Y, 1 flip-flop. So present state is only 1 flip-flop. Let us call flip-flop A. And next state A plus, next state of the flip-flop A plus, output is sum. Sum. So for the input and the present state, you will have 8 possible combinations: 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All possible combinations at the input and the present state. So by looking at the state diagram, you have to fill out what is the next state and what is the output. So let us take the first combination. Present state is 0, input is 0, 0. Okay. So present state is 0 is nothing but state S0. Input is 0, 0. What is happening? The next state is also 0, output is also 0. You can look at this combination. Present state is 0, state S0. Input is 0, 0. This one. The next state is also 0, output is 0. So next state is 0, output is 0. You are filling like this. Now present state is 1, input is 0, 0. So check the state diagram. Present state is 1, input is 0, 0. It goes to the next state of 0, output is 1. Okay. So next state is 0, output is 1. Next combination is present state is 0, input is 0, 1. Present state is 0, input is 0, 1. You can see the next state is 0, the output is 1. Now present state is 1, input is 0, 1. Present state is 1, input is 0, 1. You can see the next state is also 1, output is 0. So next state is 1, output is 0. Now the next combination, present state is 0, input is 1, 0. Present state is 0, input is 1, 0. This combination, the output is 1, the next state is 0. So next state is 0, the output is 1. I am writing next state is 0, the output is 1. For this combination, present state is 1, input is 1, 0. Present state is 1, input is 1, 0. That is this combination. The next state is retaining in the same state, that is 1, output is 0. So next state is 1, output is 0. Now present state is 0, input is 1, 1 combination. Present state is 0, input is 1, 1 combination. It goes to the next state 1, output is 0. So next state is 1, output is 0. Finally, present state is 1, input is 1, 1 combination. So present state is 1, input is 1, 1 combination, that is this combination. The output is 1, next state is 1. Both are 1 and 1. Next state is 1, output is 1. So now what we did was, we are completing the state table by looking at the state diagram. Now we have taken D flip-flop is our choice. Therefore, input to the D flip-flop is same as the next state only. So whatever is there in the A plus, you are writing as it is. 0, 0, 0, 1, 0, 1, 1, 1. You are writing this as it is. This completes the state table. Now what you need to do, the next step is, you need to find out the equation for sum and equation for input to the D flip-flop. These are the two pending things. Once you complete these two things, then you can draw the implementation. Okay, so for this one you have to use a 3 variable Karnaugh map for sum and DA. To find sum and DA, you have to use 3 variable Karnaugh map because you are having 3 possible combinations here. So x, y, a, 0, 0, 0, 1, sorry, 0, 1, 1, 1, 1, 0, 0 and 1. So let us do for sum first. You can see sum is 0, 1, 1, 0, 1, 0, 0, 1. That is minterm 1, minterm 2 is present. Minterm 4 is present, minterm 7 is present. This is the combination of XOR gate. Because XOR gate, you know, it's an odd gate. Whenever you are having odd number of input, then the output is 1. You can see for this combination 0, 0, 1, the output is 1. 0, 1, 0, the output is 1. 1, 0, 0, the output is 1. 1, 1, 1, output is 1. In all the 4 combination, whenever input is having odd number of ones, then the output is 1. Whenever the input is having even number of ones, then the output is 0. Therefore, sum is nothing but a simple XOR gate. X exclusive OR with Y, exclusive OR with A. Completed. Okay. Next you have to do it for D flip-flop. Input to the D flip-flop, DA. So, here X, Y, A, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. Now minterm 4 is present, sorry, minterm 3 is present, 5, 6, 7 is present, 5, 6, 7. So you can give this combination. You can give this combination. So from this, what is DA? DA is nothing but X into A plus YA plus X into Y. This combination will give you XA, this combination will give you YA, this combination will give you XY. So like you can see, if you give X, Y and A as an input to the full adder, it will give you the sum X exclusive OR with Y, exclusive OR with A, and the carry is the DA input. Okay, so for implementing this, already we have did the sum. Sum is nothing but X exclusive OR with Y, exclusive OR with A, you know. DA we got XY plus YA plus XA. This is the DA you are having. This is the DA you are having. So, for implementing this circuit diagram, what you exactly want is one single full adder is enough. And one D flip-flop. D flip-flop input is DA, output is A bar. You will have a synchronized clock. This is a sequential circuit. So clock is compulsory. You will have a clock. This is your full adder in which X, Y and A is the input. The output is sum and carry. The sum output will come as a output. This carry output will be coming to the D input, and this A, whatever you are having, is the carry storage which will be fed here. Okay, and for this X and Y input, what you can do is you can use a shift register. Say for example, if you want to add a 4-bit number, you are having 4-bit shift register. 4-bit shift register which is having X0, X1, X2, X3 given to the X input. This is for addend bit, and for augend bit similarly you have another 4-bit shift register Y3, Y2, Y1, Y0. This is for augend bit. So already we know what is the operation of the shift register. For every clock pulse, right shifting will be taking place. First, at the first clock pulse, X0 and Y0 will be fed to the input X and Y of the full adder. Initial carry will be given to the carry input of the full adder. Sum will come out and carry will be given to the register. which is acting as a carry for the next stage. So when x1 and y1 are given to the full adder input, the previous carry what we got from adding x0 and y0 will be stored here, and that will be given to the input, carry input for the full adder. Okay, so this is the design of serial adder using Mealy machine model. Okay, so but we want to add 4 numbers. We are first storing the 4 numbers or 4-bit binary numbers in a shift register manner. So for every clock pulse, shifting will happen, and that will serially getting input entered into the full adder circuit. Okay, so we are using 2 4-bit shift register for storing the addend and augend, which is directly given to the x and y input of the full adder. Carry input of the full adder is your A, which is the output of your D flip flop, and full adder is going to compute you sum, which is the direct output, and carry, which is the input to the D flip flop, because DA is nothing but XY plus YA plus XA is nothing but the carry of the full adder. Now since it is a synchronous circuit, you are having clock, external clock, which is common. Only one flip flop is available, so you are using only one clock. Okay, so this completes the design of the serial adder. When the question is for design of the serial adder, we are expecting you to draw the state diagram, explain the state diagram clearly, draw the state table, and take the K-map of the state table and implement the circuit diagram. So you can see in implementation we are simply using a full adder and one single D flip flop with a shift register for storing the addend and augend, which completes the shift register operation. Okay, so thank you. In the next